In this session, we will discuss RLEs, or run-length encoded vectors, from GenomicRanges. Run-length encoding is a way of representing very long vectors, where some elements are the same. This is a form of compression of the very long vectors, and whether or not the compression works depends on the type of data we are looking at. This type of compression is particularly interesting for representing signal over the genome, where the signal is only non-zero in a small part of the genome. That's true, for example, for RNA sequencing, where we are only supposed to have signal over transcribed regions. It's true for chip sequencing, and it's true for many other applications. The standard thinking of the standard way of getting the standard example of an RLE in genomics is a coverage vector. A coverage vector is something that comes out of high throughput sequencing, and it details for each base in the genome how many short reads covers that particular base. Okay, enough talking. Let's see some examples. It's gonna be a little bit easier to see it in practice. So let's first load the library. And let's construct an RLE, which we do with the capital RLE constructor. So we take a single vector, and we get the RLE out of it. So let's look at it. So what it has done now is that it says this vector starts off with 6 with the value 1, and the value 1 is repeated 6 times. Then the value 2 is repeated 5 times, the value 4 is repeated 2 times, and finally the value 2 is repeated 1. So here we can see we have something called lengths, we have something called values, and we access them using run length of IL and run value of IL. This is just a way of compressing the vector, and this is a compression in this case here because we have taken 14 numbers and compressed them into 8 numbers. So this compression makes sense if the same number occurs in the vector right after each other. We can take our run length encoded vector and convert it back to a normal vector by as numeric. We get the original vector out. There's also something to make the confusion total. There's something in base R called RLE, which is also a run length encoded vector, but has a completely different API. So think about this. You have your run length encoded vector, which is now coverage or signal across the entire genome. And very often you want to do operations where you have a set of genomic regions and you want to do something over them. So let's simulate that. You use this with you do this with the aggregate function. But let me take an example. We take an iRanges. Let's say the start is going to be 2 and 8. And let's say the width is equal to 4. So this gives me a certain subset of the RLE. And I can now aggregate. I take my run length encoded vector. I take my iRanges. And as my function, I could take the mean. I get 2 numbers back. And this is the mean of all the elements that are in the 2 different ranges. So it's the mean of let's say we take our original vector. We got that by saying as numeric of IL, and we take the mean of vector 2 to 5, index by 2 to 5, mean of that, and from 8 to 11. So this could, for example, compute average signal across a set of pre-specified genomic regions of a coverage vector. You can construct a coverage vector out of iRanges. That can be useful sometimes. So let's say you have our iRanges. Let's make a new iRanges. So I have these overlapping intervals, and I can say what's the coverage of this, by which I mean how often for for integer number 1, how many of these ranges is it part of? For integer number 2, how many of these ranges is it part of? And I get this run length encoded vector that goes like first 1, 2, and then it's 3 for a little while, and then 2, 1, because of the structure of my iRanges. Of course, I could do this with GRanges and genomic indexing. We're going to look at that a little bit later on. Sometimes you have a coverage vector, you have an RLE, and you really want to figure out areas where this vector are big, and I want to get that back as like intervals. The way you do that is you use the slice function. So you can think of the coverage function as giving you kind of a function along the genome, and now we slice the top off. So let's take our RLE from before, and let's slice it at a value of 2. So now we get a views back, but let's ignore the views for a moment. We get a single integer from 7 to 14, and these are all the positions, and in this case there's a single interval containing all of the positions where the vector is greater than 2. Greater than or equal to 2. We could do the same thing with slicing it at a little bit higher up, then we get a much smaller interval. So we got back a views object, and this is completely the same, and in a way exactly the same as the views object we have discussed for BS genome objects. So we have one potentially very big object, which is the run length encoded vector. Think about vectors across the entire genome, and we basically have indexes or intervals which subsets this very long vector. And we do that using this views constructor, but now instead of having a view on a genome, we have a view on a run length encoded vector. We can instantiate our own views, of course. And once we have a view, or we have a set of views, let's make a set of views. We can compute functions on these views here. So for example, let's say we just want to take the mean of the view, and this is basically the same as what we did with the aggregate example above. Let's do the same thing with GenomicRanges. Instead of iRanges, now everything is on chromosome 1, and we do a coverage of that. It was a little bit of quick typing. And we now get back something called an RLE list, because we have one RLE for each chromosome. In this case, we just have a single chromosome, but if it was normal human data, we would have like many more chromosomes or contexts. But here's it's a single one, and inside of that we have an RLE. When we have a genomic range like this, or an RLE list like this, we can instantiate. We can again instantiate a view on it. And now we give it, like, let's say, let's view it on the G ranges we had before. No, let's view it on like G ranges. Chromosome 1 and ranges and iRanges 3, 2, 7. So now we get an error back. It says that the ranges list must be a ranges list object. This is a type of object we haven't discussed from GenomicRanges. But aside from G ranges, there's these things called ranges data range data and ranges lists that really are more, they were an attempt at providing a tree-range-like object. It was by some accounts successful, but it hasn't really stuck around. We still see these objects being around here and there. So the way you really solve this is you coerce it. So you take this tree-range and you just like say, okay, let this be a ranges list. And now we have this RLE views list, and let's take what we see on chromosome 1, and now we have a views exactly as we wanted from position 3 to 7. It's a little weird that tree-ranges doesn't work directly as input into views. I would consider that a kind of a bug, and I'm definitely going to discuss that with the Bioconductor people. So now we've learned about run length encoded vectors. We have learned that we can have them both on the integers, but we also can have them on the genome. We can also have we don't just need to have run length encoding of integers. We can have run length encoding of logicals or even characters or logicals. Actually, come to speak of it, if you look at a G-range, you can see that the seq names or the chromosome names are, we can now recognize that these are run length encoded vectors because we often have all the ranges on chromosome 1 next to each other. We have learned about how to compute on them using aggregate and views. We have learned how to convert a G-ranges into a RLE by coverage, and we have learned we can slice off the coverage.